the first part of the second lecture. This is, and we are classical now. The afternoon is more relaxed, less than
Yes. Yeah, thank you. So, yes, I'm going to talk now about classical ways of describing many-body physics, and these classical ways will be based on something that are called tensor networks that I want to introduce. And the tensor network language is a language that is very much motivated by quantum information theory, so it's a quantum information theory language. And so you will see that it's also, there's a kind of big motivation to describe quantum many-bodies physics, as I was presenting this morning, to address some of the problems that I was mentioning this morning with the language, with this classical language of tensor networks. And the motivation is twofold. So on the one hand, because with this language you can build classical algorithms to describe quantum many-body systems under certain conditions. And so these conditions are typically ground states of gap Hamiltonians or thermal states of local Hamiltonians. And there is a second motivation, which for me is much stronger than the first one. It's not so much because there's some numerical methods, it's because it is a language to describe physical phenomena in a very different way from the one that people used in the past. So maybe some of you have heard about the description of phases of matter or phase transitions in terms of Landau theory, in which what you do is that you have one of these quantum many-body physics, and then you have some low temperature. Then you can sometimes look at the symmetries that your Hamiltonian has, and it turns out that whenever you go through some phase transition, some of the symmetries are broken. So meaning that the states, the ground states of your Hamiltonian are degenerate, and some of these, in this subspace, there are some states which don't fulfill the same symmetries of your Hamiltonian. So the Hamiltonian is invariant under some symmetry transformation, whereas your ground state is not invariant under this symmetry transformation. We say that there is a symmetry breaking there, and so Landau figured out how you can describe many phases of matter and phase transition in terms of symmetry breaking just by looking at the symmetries and see what are the ones that can be breaking, and depending on the one which we're breaking, then he had different phases in the phase diagram, and then we can do some mathematics, expansions, and so on. So there is a whole theory like that. However, this describes certain phases in which there is symmetry breaking. However, there are some phases of matter in which there is no symmetry breaking at all. And so this cannot go into the description of the Landau theory. And as you will try to argue, then with this tensor network is a kind of an extension of Landau theory, which allows you to describe not only phases that don't have any symmetry breaking, but ask some other questions that people have been asking during the last 5 to 10 years about many-body physics that can be now as answered with these tensor networks. And one of them is the classification of phases with respect to certain symmetry. So I will mention that towards the end of today's lecture. And the basic idea is that you would like to have a periodic table in which you will have the different possible phases of matter, and whenever you have a system, then the system has to be in one of these phases. It will include Landau phases, but it will include some other phases, and will give you a classification. And this classification has been performed in terms of these tensor networks. That's one application of these tensor networks. And there are some other ones. I mentioned the ones related to this quantum gravity, and so these wormholes, extraction, the paradox. So tensor networks have been used also in that language. Tensor networks are used now in machine learning as well, so there are some machine learning methods that basically use tensor networks, and so on. So that's, I think that it's a good idea to, since we talk about many-body systems, to explain in the kind of some detail these tensor network techniques, which is relatively easy with the language that I introduced this morning, to tell you how you can build out of that some methods to solve problems numerical, but also how you can use them more from the analytical point of view in these numerical calculations, in this classification, sorry. So, I have to just say from the beginning that I'm aware that there are many techniques for describing many-body physics with classical computers, and they include series expansions. So you have, for example, sufficiently large temperature is e to the minus beta h that I wrote. You can expand in series, a Taylor series expansion, and then you can compute trace of observables in this series, and if this converges, then these are good methods. There are some other methods which are based, for example, well, they're exact diagonalizations. You can want to compute the ground state properties of your Hamiltonian, then you write the Hamiltonian as a big matrix. It has 2 to the n by 2 to the n matrix. If you are dealing with qubits, you can diagonalize and find all the properties, but however, this is restricted to small systems, so typically you can go up to 20 qubits for that. There are better methods than the exact diagonalization. One of them is Lanczos. It's a popular one, in which what you basically do is that you take a random vector, and then you apply the Hamiltonian to this random vector, and then you get another vector. And then you apply again your Hamiltonian to the random vector, and then you get vector. Then you make a series of vectors. This spans some subspace, and then you expand the Hamiltonian in this space. You compute the expectation values of the Hamiltonian in this space. Then you have a matrix which is big as the number of vectors. You do 20, the 20 by 20 matrix, and then you diagonalize this matrix, and then you find the ground state, and this gives you an approximation, actually a very good approximation. And the advantage with respect to the exact diagonalization is that instead of dealing with matrices, which are 2 to the n times 2 to the n, you deal with vectors, which are 2 to the n. So you get a factor of 2 to the n, still exponential, and people with Lanczos can go compute ground state properties of the order of 30 particles, or exactly. Now you put symmetries on top of that, so you have a model like the one that I wrote this morning, like the Heisenberg model. Heisenberg model has SU2 symmetry, and therefore the ground state with respect to symmetry has to be in a subspace that has smaller dimensions, so you can use the symmetry to gain a little bit of, not to work with this bigger matrix, because you work when you have a block diagonal matrix, you can work with one block. And for that, people, I think the record that I know, they have been able, and using also translational invariant, rotational invariant, things like that, they can go up to 40 qubits or 45 qubits, an exact diagonalization. That's the limitation of this Lanczos method. The Lanczos method can be also used for time evolution. So you want to describe the evolution of a state, you start with state, and then naively, you would like to compute e to the minus I h t acting on the state. So the state is a vector, a 2 to the n vector. And then you can diagonalize your matrix and exponentiate, but this is very expensive. So in particular, it's much better, since this Hamiltonian is local, to write the Schrodinger equation and to solve like a set of linear differential equations. And so you don't have to compute the Hamiltonian, you have to apply to the state with ODEs and things like that. And so this is scaled better, and the limitation is of the order of 30 qubits. And this is why you look at Google website, and they have a simulator of a quantum computer that works up to 30 qubits, because they use these methods, exact methods, to simulate the real quantum computer, even including noise. And I know some other companies have emulators which all can also, use this kind of classical method, but they're limited to a few number of qubits. And in fact, you use one of the quantum computers that are available today, and many of them have the order of 20 or 30 qubits, so actually you don't need the quantum computer itself, because you can use these emulators, because these are good enough to do the research, do the same thing as a quantum computer that has 20 to 30 qubits, just based on this exact method. There's also, perturbation theory. You have some perturbation and so on. There are many theories. One of the most popular especially in high energy physics and condensed matter physics, are Monte Carlo methods, in which, so maybe I explain this a little bit, because this will be interesting tomorrow. So this is two classical tensor networks algorithms. So I was mentioning the Monte Carlo, and so remember that we have a thermal state. We describe it in terms of the Hamiltonian and the temperature in this particular form. And at the end, we are interested in computing expectation values of some observable with this state. This is what we call O. In the problem that we formalize it to some precision, epsilon, for some temperature, for some sizes, and so on. And one possibility is just rewrite. Let me assume that this O is a local operator. You can do it for more general, but local operator. And without loss of generality, it can be an operator which is diagonal on the computational basis. So what this means is this could be, for example, a sigma C operator, which was diagonal like I wrote it before. But if it's, you take another one which is sigma x, and you work with the eigenstates of the sigma x basis, which is another basis, and in that basis it's diagonal. It means that in that basis, if I take the trace in that basis, the trace is the sum with respect to all elements of the basis. So let me write n1 and n, and then I could take like n1 and n, this all go n1 and n, and this will be divided by the trace. So I mean, trace of rho is equal to 1, so I can divide by trace of rho here, and so I can put this n1 and n times rho n1 and n. And I mentioned now that this O is diagonal in this basis, so I can take it out. So I can just write this like n at the position I, where O is acting in I. And let me call this a number, right? There's some sandwich between some state and some operator is a number, and it's a positive number because rho is a density operator, and in fact, it's a probability distribution, so I can call it P of n1 and n. Down there, we have also the P of n1 and n, and then this is equal to the sum of P of n1 and n times let's say n I of n I divided by the sum of P n1 and n. And so that's just exactly the same formula, just rewritten in some form. But now you see that if this is an expectation value with a classical probability distribution. So if I can sample this probability distribution, so if I can just sample values of this n, and for each sample can compute this quantity, and I sample many times, we know with the law of large numbers again, that this will converge to the expectation value, and this will converge very fast, like 1 divided by the number of square root of the number of samples times the variance of this operator. So this, if I have m samples, and I can sample with respect to this distribution, this will converge to something that has an error 1 divided square root of m. And so you see that classically, as long as I can sample according to these probability distributions, then I will be able to compute this very efficiently, because if you give me some prescribed error epsilon, then the number of samples that I will take to take will be 1 divided by epsilon squared. Very efficient. So the question is whether we can sample that. And you will look at what it is in sample. Now, the first thing is that you have to find a way of sampling, and there are ways in the market sampling. So one of them is Hastings methods or with the Metropolis algorithms and things like that. And so for all these methods of sampling that we know that can be used, the idea is that you sample 1. So this means that you have qubits in your lattice, you put just 0, 1, 1, 0, 0 randomly. Just take a random sample. And then you flip some of the qubits, and then you compute the probability, this number, for one of the configurations and for the other configuration, and depending on the probability, then you accept or not accept. So you compare the probabilities. If the probability of the second one is larger than the first one, you accept it, and if it's smaller, then you accept it just by throwing another random number with certain probability. So that's what all these methods do. So this means that at the end, I mean, these sampling methods have to fulfill 2 properties if you want to use them for that. First of all, you should be able to compute this probability, because every configuration, you have to compute the probability in order to know whether you accept it or not. So number 1, should be able to compute this number. Number 2, you have to be lucky, because these samplings, Metropolis and so on, they don't ensure you that they will be ergodic. So they don't ensure you that you will sample according to the whole distribution you've spent some time at sampling. So there are conditions for this to happen, so that have been studied in classical statistical mechanics and so on. So typically very difficult to handle, but sometimes may work, and in practice they work very well. The bottleneck is how to compute these probability distributions. So how do you see it? Well, this probability distribution is some matrix element of some exponential of some operator. The only way that we know how to do this exactly is to take the matrix and exponentiate it and look at the matrix element. But exponentiating this matrix is 2 to the n by 2 to the n. So we will have to exponentiate the matrix, which is huge. We'll have to, for that, compute eigenvalues, eigenvectors, and we'll be limited to the 20, 30 to do the exact computation. So this has a limitation. However, some people in the last 40 years or 50 years figure out that there are some particular cases for which you can compute this probability distribution. Well, it's even a little bit more than that. So what they realize is that maybe I cannot compute this, but I can write this probability distribution as a product of other numbers that I can show that they are positive. So what they do, basically, I don't want to say that too much, but they write e to the minus beta h as e to the minus beta h divided by L, multiplied L times. So these are L times. So this is this operator here. This is the row, which is here. And then you can put the identity operator here, the resolution of the identities. You can put here some m, I write it as a vector, m1, and everywhere the identity. So at the end, when you plug this here, let's look at the first, let me call this m here to simplify the notation. So you see that the sort of things that I will have now, that this is equal to the sum, the original sum over n. Right? These are all the configuration. But now I have also the sum with respect to m1, sum with respect to ml, because I put resolution of the identities at the beginning, and so there will be something like m times e to the minus beta h divided by L times m1 times the same thing with m1 and m2 and so on. And in the denominator, the same thing, until here this expectation value that I told you before, n o n. And now, if you're lucky, well, first of all, if L is very large, then we can, this is like, you can expand in Taylor expansion. So this would be like the identity minus beta h divided by L. So the identity will give you a delta function, and then you will have here something to compute some expectation value of h with product state, which is very simple. So for L sufficiently large, it is possible to compute that. And if it turns out that this quantity is positive, so you can prove that these quantities are positive, then you see that now you can call all these some q of depends on n, on m1, on ml, which is positive, can be interpreted as a probability distribution itself. And therefore, what you have to do is to pay a price. You will not have to sample only n, but you will have to sample also m1, m2. So you have to take L copies of your system and sample all of them at the same time. But then you can use Metropolis because you can compute the Q, because now these are can be computed analytically, and therefore you will be able to use Metropolis. So if your problem fulfills that, so if the problem fulfills that when you find a basis in which all these elements are positive, then you can use Monte Carlo, and this Monte Carlo you will be able to compute. You will still be facing the second problem, which is ergodicity, but in practice this works very well. But this is why people in condensed matter physics, they use this method whenever they can. They find Hamiltonian that has this property, they use this method, and this works very well. So in a sense, if the problem fulfills that, it would be in BPP, in the language that we had before, classically simulatable. If people here working on lattice theory, high energy, there is a very similar procedure in terms of the path integrals, that you have also the same thing that you can rewrite in terms of sampling with positive numbers, and then that's done. However, of course, this condition, this here is a non-diagonal element, and that non-diagonal element doesn't have to be a positive number. It can be negative, it can be complex, it can be anything, so nobody ensures you that if I give you a Hamiltonian, you will be able to do that. And then people in the jargon of Monte Carlo will say that you have the sign problem, and therefore you cannot use Monte Carlo methods. Okay? And this happens generically, And this happens in Hubbard models, happens when you have frustrated, it happens when you have in high energy physics, in lattice gauge theory, you have some chemical potential, and so on. This happens, and therefore this method is not possible, is not useful. But still, you see that there is a very powerful method for certain kind of Hamiltonian, for certain kind of problems for which there is no sign problems, and people use it in practice. So what I want to do is now to concentrate on some of the methods which will be based on something different from the here, will be a tensor network, which in some case in which there is the sign problem, then it still can work, or may work, but also, as I mentioned, I will use them for classification. And tomorrow, in one of the lectures, one of the quantum algorithms, what it will do is whenever there is a sign problem, then it will use a quantum computer to compute this number. And so if I can compute this number, then, as I mentioned before, I can use the sampling methods. So whenever I would have a sign problem that I cannot use this in a classical computer, I could use a quantum computer. With a quantum computer, I will still sample, take classical samples like 0, 0, 0, 1, 1, 1, 1, 0. And in order to see if I accept the move or I don't accept the move, I will use the quantum computer. The quantum computer will deliver this number. With this number, I will accept or not, and therefore I will be able to use Monte Carlo with a quantum computer. That's related to the question that there was this morning about the hybrid algorithms. This would be a hybrid algorithm because it's using the classical, it's called quantum Monte Carlo, but it's a classical method in the language that I'm using, the classical quantum Monte Carlo, but assisted with a quantum computer to circumvent the sign problem. That's an example. But anyway, so I want to concentrate, as I mentioned, in these tensor networks, and so now, from now, I will concentrate in this technique based on tensor networks. And in this tensor network, like in all these many-body physics problems, if you start writing formulas, it gets extremely complicated. So now I will have to fill out the black one many times just to express what I want to say. However, there is a way around to avoid all that. It is to use some graphical language. So what I will do is I will introduce tensor networks and this graphical language. And for the ones who are not used to this graphical language, as a step, I hope that you're able to follow, and that then you can follow the rest just with this new language that I'm using. But this, I mean, if you use it a couple of times, it's very natural and avoids writing very, very big equations. Like if you would write Feynman diagrams, just write an integral, blah, blah, blah. Okay, you would never do that. We'll do some. So here it's very similar to that. So I want to use this language. So this is one tensor network. Okay, and so the basic idea of tensor networks, the basic motivation, is that you remember that I told you at the beginning that ground states and thermal states of these many-body systems, they fulfill the area law. So I'm going to leave out the dynamical problems. These dynamical problems cannot be solved with tensor networks because they have too much entanglement, and this cannot be described. So this will be the subject of tomorrow's quantum computer addressing this problem. So today I'm going to concentrate on the other two problems, thermal equilibrium, ground states, or finite temperature. And so this now, if you have a ground state of a many-body system or a thermal state, it's not a random state in Hilbert space. So if you would take now coefficients, 2 to the n coefficients, and take random numbers for these coefficients, you will get a vector in Hilbert space which has dimension 2 to the n. But this will never be a ground state of a Hamiltonian. The ground states of local Hamiltonians and very special. And why? But because they fulfill this area law. Random states don't fulfill the area law, but these ground states or thermal state are not random states. They have many, many special properties. So what we typically do is to say, well, if this is the Hilbert space, and these are all the states there, they're all possible superpositions, the ones that correspond to ground states of many-body systems of thermal states, which would be mixed states, are in this corner of Hilbert space, in a very little corner of Hilbert space, and that's the corner where the signature lives. In fact, I mean, there is easy to see that most of the states of Hilbert space are never used and will never be reached by nature. It would be impossible. Now, don't care about them because they will not, and they are completely boring. Because you measure expectation values, they are all zero. The trace of, they give all zero. So nature, physics, takes care in this corner of Hilbert space, which are the states that fulfill this area law to the index in the way that I mentioned the other day. And it shouldn't be surprising that nature is in a corner, specific corner of Hilbert space. You can do it without knowing anything, just by counting arguments. So what you can do, and let me tell you what you can do. I told you before that we're interested in Hamiltonians, which are local, that I write something like that. H now lambda with lambda is in your lattice. So you had your lattice, and the Hamiltonian, each of the terms, x, let's say in some region, for example, in one side of the nearest neighbors, or something like that. These are the kind of Hamiltonians we're interested in, where they're we call geometrically local. They're actual regions. Of course, they have overlapping regions, but they are in some region. And now you can count how many parameters you can put in this Hamiltonian. So the number of parameters that characterize all possible Hamiltonians of this kind would be the number of parameters that characterize a region, and this will be a constant. So you have a region like 2 by 2, and you have a dimension of this space d. It will be something like d to the power 4. So there is a constant number, here a constant number of parameters, some constant number, and then you have n terms in the Hamiltonian, so you have a constant number times n. So the number of parameters here to characterize is proportional to n of all these local Hamiltonians. However, your Hilbert space has 2 to the n parameters. Now, if you talk about the ground state depends on your Hamiltonian. So it can be parameterized by the parameters of your Hamiltonian. If you fix the parameters of Hamiltonian, it determines the ground state. So the state we're interested in, psi, depends on some parameters, and the number of parameters are also proportional to them. So this means that if you're looking at ground states, then the number of parameters of all possible ground states of interesting Hamiltonians will be scaled like n. No, like 2 to the n. And this is this corner of Hilbert space, which is very, very, very small because only grows linearly with n and not exponentially with n. Now, if you would have long-range interactions, like we would have in Coulomb systems, still this Hamiltonian is too body, so this means that this will scale like n squared, still very small. And if you go to fundamental theories, all fundamental theories are local, and therefore this is true for all fundamental theories as well. So all the physics that we experience in material and math is in this corner of Hilbert space, which has very few parameters. So if we use now a method to describe many-body systems who doesn't take into account that we are concentrated in this part of the Hilbert space and try to treat all the states on equal footing, then probably this will not be a good method because it's not specialized for this thing. So the idea of tensor networks is to have some language which addresses this part of the Hilbert space that is not efficient if you're out, but if you're here, you have one of the states that fulfill this area law, then it's very efficient. So you can describe the state with some number of parameters which grow only like n or polynomial n and not exponentially. So that's the motivation. And so if this is true, so you have a description now which addresses this interesting corner of Hilbert space, then you can use this description for numerics, because as I told you before, when you talk about problems in many-body systems and you have a classical description of that, you run into two problems. One of them with the exponential growth of the memory, the other one is the exponential time. So with that, you get rid of the problem of exponential memory because I'll show you, I will tell this is an efficient description. The number of parameters here for this corner does not grow exponentially. Still can grow exponential with time in the same way that also quantum computer could in principle grow the computational time, exponential time, if it's a Q&A hard problem, for example. So that's the motivation of this tensor network. It's a description addressed to this corner of Hilbert space which has little entanglement because it fulfills area law. So, I mean, there will be, I will make some statements here and there about this corner of Hilbert space and the relation of this corner of Hilbert space with the tensor networks, and I will give some not mathematical proofs of this what I'm saying, but we recently wrote a review model physics so that you can see all these proofs and everything like that, so it's interested more in the mathematics of what I'm talking about here, and also it's more precise about the statements. So my statements here are, let's say, half true, okay, so they're qualitative, and you want to make them rigorous, then you have to specify things very well, but I'm not going to do it here. So this was about the motivation. Okay, so now I'm going to describe these tensor networks, and so the idea is that what you will do is that you will write a tensor that will have different indices, few indices, maybe 3, 4, 5, 6 indices, and this tensor will describe the whole many-body state. And so this means that you will not have to work in Hilbert space, you work in tensor space, and in tensor space there will be a much less number of parameters. And so for that, first I want to just make you familiar a little bit with the language of tensors. And so what I will do is that, for example, I have a vector. Now I have to write a vector with some components, and a vector with some components will have the component 1, the component 2, maybe the component 3. I will represent a vector like a box with one leg. And the interpretation of that is that now if I take the leg here and I assign the value 1 here, then this will give me V1, the first component. If I take this leg and I assign to this leg the value 2, this will give V2, and if I go on like that. So you see, I represent the vector in an abstract way in this form, and if I want to recover the first component, I will plug here the first value, and then I will have the first vector. So of course, a vector is a tensor. It's a rank 2 tensor. It has only, let's say, one index. Now you have a matrix. The matrix is like the generalization, so it's a rank 2 tensor, so it has 2 indices. A matrix has mij, so m1, 1, m1, 2, m1, l, and so on, ml, m1, ml. So I will represent the matrix now as a rank 2 tensor, meaning that this will have 2 indices, for example, this index and this index. And so what I mean by that is this represents m, so maybe I write here m. What I mean by that is that I want to recover the value mij, then I will inject here an I and the j, and this symbol will represent this. Okay, so the moment is just working with matrices and vectors in the standard way, but I'm using some language in order to represent these vectors. Now we can multiply, for example, vectors with matrices. So you can have a matrix and a vector, and then you can multiply them, and we know that the result will be some other vector. And if you take the ith component of this vector, it is the sum of m, I, say alpha, mij, times vj, right? From I to 1 to whatever the indices runs. So typically I will call this total dimension, so D. So this would be like this is a D times 1 matrix if you want, and this would be like a D times 3 matrix. So I have like this called D. Well, anyway, so you see, at the end, if I'm multiplying a vector by a matrix, what I have to do is take each the component of the vectors, the component of the matrix, and contract them in some particular way. I have to identify the index of the vector with the second index of the matrix and sum with respect to this index. So this, graphically, what I will do is that I take the matrix I said that I have this, and the vector is something that has just one leg going out, and contracting, multiplying, the only thing that I will do is to put them together. So what this means when I write something like that is that if I want to this will be now a vector which has only one leg. This is the leg that is left. And so if I want to compute now what is the leg component I, so So what I would have to do is to put here I, and I can read it off from here. I can say that the element I here is the same element as I, and I read this. If I want to write a formula, I will say this is mi, and this index is contracted, so it means that I have to put j, take here j, and sum. And so in this way, every time that I do a multiplication of a matrix and a vector, I don't have to write anything, so I just have to put them together. So now we can multiply matrices. For example, if I have a matrix M and a matrix N, so how will I represent? Well, I will write my matrix, I will write my second matrix, and contract one of the indices. And so this is the product of the matrices, so I will not have to write. So if I want to have the element ij or ik, is mi, j, n, j, k, sum over j, and that's what it means. So by making these drawings, then I can represent matrix multiplication. But now what we can have is higher rank tensors, and these are the ones that will appear from now on.
Can you connect the two legs of the matrix?
Right, then it's like a trace. It's like a trace. Then it's a trace. Exactly, so I can compute the trace. So for example, I could do this. This is M1 and 2 and 3 product, and then the trace. Now, I can have tensors that have more indices. So I can have, for example, now a rank 3 tensor. Right? And now, for example, I can contract indices. I can put, for example, several that may be equal, like what? Like that. And I can, for example, connect them like that. And so, what is this, what I have? At the end, the object that I obtain is a tensor which has now 4 legs. These are the ones that are not contracted. So it's a leg, I could write it like that. It's a tensor like that. And if I want to write a formula for that, if I call this tensor A, this index I, and this index, for example, alpha 1, alpha 2, then the formula would be I, we call it I1, I1, alpha 1, alpha 2, A, I2, here I2, alpha 2, alpha 3, blah, 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 and the next one would be IN, alpha N, alpha 1. So it's a tensor in which this is sum with respect to all possible alphas. And so the tensor, if I put here, if I inject I1, I2 up to IN, this number, this complex number, I can compute it just by taking this tensor and just doing this sum. Now, you see that now what I could do is that I can consider a quantum state. So now I go to Hilbert space, and then I write a quantum state in this form. This would be a linear superposition of all the basis states, so I have to sum with respect to all possible I. So these are up to D, these are the physical dimension, and this could be a state. So it's a state in which the complex coefficient 0, 0, 0, 0 is the one that I put here as 0, as 0, as 0, as 0. These are the matrices. I compute the product and the trace of the matrices, and this gives me the first coefficient. The coefficient 0, 0, 0, 0, 0, 1 would be the one in which I set this, these matrices. Now this will be different. This will be the matrix with a 1 here. There's 2 indices that I contract, and then I get an even. So each of the 2 to the power n coefficients that I will compute like that can be computed just by doing traces of product of matrices. States that can be written like that are called matrix product states. So these are called matrix product state, MPS. And now you see that what is the number of parameters that I need if I want to specify a state? Well, the number of parameters is the number of parameters of each of the tensors. So in this tensor, I have, there's an index D here, an index D here, and an index small d here. So there are D times D squared parameters here. another here, if this tensor is different, if this tensor is different, this tensor is different, this is the number of parameters. N times D squared. So you see that with a number of parameters that grows linearly with N, I can represent states of Hilbert space. Now, where is the magic? Well, the magic can show that every state in Hilbert space can be represented like that. Somehow the magic or the trick is that if I go to the whole Hilbert space and I take a random state and I want to represent it like that, then this dimension that I will have to put here, which is called the bond dimension, will be exponential in N. So there will be an exponential included here. There will be two. I have to have tensors that have many elements to represent the any element of the Hilbert space. And what is the claim? The claim is that if we are in this corner of Hilbert space, it's sufficient to take some D that is constant or better that only goes polynomially with N. And so this is the first statement. That these are matrix products. I will introduce some other ones. But anyway, so that's the philosophy. The philosophy is that at the end, you write your state in terms of some tensors which have less parameters, and that hopefully, I haven't shown that, they represent the corner of Hilbert space you're interested in. And that is enough to do it with less parameters. But even more, imagine that your state is homogeneous, it's translational invariant. If it's translational invariant, all these tensors will be the same. It means that the number of parameters may not even depend on n. Or in other words, you can take a tensor, and with a tensor, you can describe a many-body state with an arbitrary number of parameters. So, in fact, if you consider, which I will consider most of the time translational invariant, but anyway, so it means that instead of working with a Hilbert space, when you have size, then it may be more efficient, more economical to work with these tensors, A. And now you know that there is a map. If I give you a tensor, which is represented maybe by 20 parameters, this corresponds to a many-body state with an arbitrary number of particles, because I can construct it like that. And so the idea is to work with these tensors and develop quantum mechanics in terms of these tensors and never do something like that. So, of course, what I could do is to talk about these tensors, and if I want to compute some expectation value, some observable, I can compute these coefficients, and with that I know how to compute the expectation value. However, I will have to pay a price because I have to compute an exponential number of coefficients. However, there might be a direct way in which, with giving the tensor, I can compute these expectation values without having to resort to this formula, directly with something that doesn't scale with n, or that scales linearly with n. And so that's the whole philosophy of tensor networks. First, to have an efficient description of a many-body system in terms of these tensors. Now I'll generalize in a second. Second, to show that they correspond to the whole the corner of the Hilbert space that you want to describe. And third, and more difficult, is to find ways of, once you have the tensor, you don't write the state, you don't work in Hilbert space, you work with tensor. If I give you the tensor, how can you get the physical properties of this tensor? How can you see if you have topological order, that you have a critical system? How will it show? How it will show up in the tensor? Now, in the Landau theory, actually, what will happen is that this tensor will be a simple vector. They will not have other indices. And this is why people, they look at order parameter, they look at the vector, and with the vector, they have the properties of the system. So here, you will have tensor, you have more indices, but this covers much more possibilities of physical behavior. That's the idea. So, just 1 minute. So, as you know, here, I have if you look at the drawing that I'm doing here, there is a geometry behind this drawing, which is that I'm writing something next to each other. So somehow, there is a one-dimensional geometry attached to these matrix product states, and indeed. So you see that you could think that you have like a one-dimensional lattice, where you have different qubits, and to this one-dimensional lattice, then you are contracting these tensors according to your geometry. You assign one tensor to each of the particles, and now once you assign a tensor, then you contract it according to the geometry. And this tells you how to go to higher dimensions. So you have a two-dimensional system or a two-dimensional lattice, something like I was drawing before, with whatever geometry. The procedure is the same. You take to each of your lattice sides. For example, you have the, as I mentioned, spins in the vertices. You assign a tensor to each of the spins, and this tensor has, on the one hand, the real index, the physical index. This index is the I index, so this is like the one on the computational basis. This is the physical index that you're interested in, the physical space you're interested in. So it has a physical index, like we represented like that. This is the I. And then it has indices corresponding to the vertices of the edges of your lattice. For each edge, you have a vertex. And now you want to build the state corresponding to that. Then you put the tensors in the form of the lattice and then contract it according to the geometry of the lattice. And if you do that, these tensors will generalize the matrix product states to higher dimension for some historical reasons are called PEPs, projected entangled pair states. Projected entangled pair states. I mean, I'm not going to explain you that connects with quantum information because it will take me a bit too long. Okay, so again, the idea so far is that we have now a way of describing many-body states that is very efficient because I just have to give you a tensor, and out of this tensor, if you want, you can compute the coefficients. But we will never compute these coefficients because this is what we try to avoid. And now the question is, how can we look at the properties, or how can you extract the properties or compute expectation values just with the tensors without having to resort to something like that? And second is what is the connection with this corner of Hilbert space? So how do we see what is the connection of this Hilbert space? I will not be able to show it, but I will give you some qualitative ideas why this is like that. So it's time. Yes. Okay.
Che le domande fossero previste forse dopo il
Questions are not after the
We can ask questions now.
I have a question. Should I keep it or can I ask it? I'm the chairman. If you are not making any difference between upper and lower.
No.
But you can do it if you make some sort of arrows so that
Exactly.
you connect all of that.
Exactly.
And the matrix is something with one arrow, one
Exactly. So entries also one on the left and one on the right indices. You can have covariant and covariants like the standard, but I will not need it here. This is why I didn't want to introduce this notation.
Okay. So if there are no more questions in this session, we can have the coffee break and we reconvene in how long time? 30 minutes. Okay.
Sì.
This is traditional series of lectures full of people, and this shows that the interest is always important. I'm very happy that we have traditional lectures that these times I see on the agenda too. I'm not an expert. Talks about application of quantum computing, which is a very interesting and in particular this period hot topic. As an NFL director, let me just mention that we have a national project funded by this European Residence Program dedicated to high performance computing. There is an important spoke about quantum computing, and indeed also we have a lot of activity both from the modern theory and the experiments. So really happy this topic is covered in this lecture. So we'll take more time.
Okay, thank you. Okay, so I will. So the plan for today is give you a little bit more techniques with this tensor network, so how this works in practice, so they come to compute expectation values and so on. Then I will spend some time talking about this efficient description, so showing why is this related to this corner of Hilbert space that I mentioned before, why this is an efficient description. And then at the end, then I will talk a little bit maybe about classifications or topological phases or something like that. I will not have so much time for that. And I also wanted to tell a little bit about the continuous limit, so how to get these tensor networks in the continuum limit, but I'm not sure that I will make it. Anyway, so now I will work to make things simpler with this one-dimensional, with what I call matrix polar state, but most of the things that I'm saying can be done in higher dimensions with these steps. And whenever it cannot be done, then I will tell you, so what is the difference and so on, so that you don't think that everything works right like I'm saying, so one has to be careful. So I remind you that now we have a state on Hilbert space, and we will have one of this QD chain or spin chain. Then the state we will represent as a tensor network. So instead of writing something like that, then what I will take is this drawing that has to be understood maybe like that. That has to be understood in the way that I told you before, which I remind you. This means that if you want to compute the coefficients of this state in a basis, the only thing that you have to do is use the coefficient 0, 0, 0, 0. Then you have to plug here the 0, 0, 0, 0, and contract these tensors, and this will give you a complex number, and this will be the coefficient 0, 0, 0. You want the coefficient 0, 0, 0, 1, then you put here 0, 0, 0, 1, then there will be these matrices, that you multiply the matrices, and this will be the 1. But we don't want to do that, because there are exponential number of coefficients, and that's exactly what we try to avoid. So the question is, how do we compute an expectation value, now using this language of the tensors, directly, without having to resort to Hilbert space in tensors. And so the idea is how I compute psi or psi, where this is acting on some of the qubits, could be one of the Pauli operators, on anything. And the idea is to do it just graphically, because this is a contraction itself. Do you see that I have here this vector, this vector, then I have an operator, and an operator is a matrix. So it has an index and an output index. And this is another vector, which is contracted from the other side. So you see that we could do that just by taking, this would be the psi. Then we put here psi complex conjugated. Also contracted. And then at the position I, we put this tensor, which is a matrix. So at position I, which will be here, I put this tensor, which is this O, and the rest is contracted. And so this would be the tensor network description of this expectation value. Now we can recognize that what I can do is that I can merge indices. For example, if I have something like that, I can represent it as a single tensor with two indices. And two indices, I can represent it as a bigger index. So for example, if this index runs from 1 to d, and the other one runs from 1 to d, then I can have a single index that goes from 1 to d squared, like the 1, 1, associate 1, 1, 2, 2, and so on. And so I can write it as a single index. So this is just which has more, which has higher dimension. So you see, I can take this part of the drawing, and this has two indices to the left, one index on the right, and there's all that is contracted that I have to take into account. So I can write it as something like that with this index, this big index. So this big index and this big index correspond to this one and this one and this one and this one. And the second one I can do the same, and I can continue doing that. And the last one will be connected to the first one. And this is a matrix multiplication according to the language that we have. Okay? So this means that at the end, if I want to compute some expectation value with these tensors, the exercise that I have to do is that I have to take this tensor, that's the original, the one that I gave you, take the complex conjugated tensor, put it here, to make out of that a single matrix. And for the special one, when I'm computing the expectation value, I have to do the same thing. And write it as a different tensor. So maybe that's like that. And at the end, I have the contraction of this tensor. So, again, what is the computational time to compute this expectation value? Well, we have to do some matrix multiplication. And the matrix multiplication, as you know, the number of the computational time scales like the index to the power cube. So this index has dimension d, this index has dimension d, this d is d, the index has d square. So we'll have to do matrix multiplication and matrix multiplications, which are of d square times d square matrices. So the computational time will be n d to the power 6. And so it's nothing exponential here. So as long as you have some one dimension, then that's the whole idea. Not to go to Hilbert space, but to compute things directly in terms of the tensors, whenever you want to compute expectation values, and so on. Now, so the next question, practical question, is how do I find these tensors? If you give me a Hamiltonian. And so the way of computing these tensors, the way that people typically use, is a variational method. So what you do is you say, okay, so you give me a Hamiltonian, H, which is the sum of Hamiltonians. And what I can do is that I say, well, let me compute what is the expectation value of the Hamiltonian with some state psi. And this state psi has the different tensors. So this contains, let me write some A, meaning that this has certain tensors. And each of the terms is of this form. So each of the terms, you can compute it in this particular way. So you have n of them, because there are n Hamiltonians. So you will have to do this computation, which will be like n squared times, or something like that. And then you see that this would be some energy that depends on the tensors A. And so now you can use the variational principle, which is that you can minimize with respect to A this energy, and you do the minimization, and you find the argument of this minimization. This will tell you what, like any other variational method. Now, like variational methods, when you want to compute minimizations, then sometimes these minimizations, since they are multivariables, they are not easy to compute because you get a stack. And so there have been people who have developed some methods and even have proved that they cannot get stuck if you do it some particular way. And now, if you take a Hamiltonian in one dimension and you have a gap in the Hamiltonian, then people show that if you do this in the right way, you will be able to find some tensors that the dimension of these tensors here is enough if it's proportional to n. So the number of computations that you will have to do will be n to the 6 or n to the 7, and that you will be able to find the ground state, and once you have the ground state, you will be able to compute the expectation values. And so that's the way that it works. Now, 2 comments. This is true for 1 dimension. For 2 dimensions, it's more complex, and there are not such a proofs. There's just practice. So I will not have time to tell you, but the idea is that now you have tensors in 2 dimensions in a lattice. Each of them has an index pointing out instead of an index pointing up, like the ones that we had at the beginning, like these ones here. Now they have indices according to the plane, one coming out, which is what we call the physical index, and you want to compute some expectation value, then you have to put the complex conjugate, put the observable, and then contract everything together. So now instead of contracting something like that, you have to contract a 2-dimensional structure. And so people have developed algorithms to contract this 2-dimensional structure, in practice in an efficient way. In theory, one has not proven that they will always work. And so that's why when people talk about tensor networks in higher dimensions, they say that they work in practice, but there is no proof that they will work in theory. What works in theory is that they still give you an efficient description. However, when computing expectation value, it may happen that it takes a long time, that the time grows exponentially. It cannot be proven. Okay, so once I have that, you see. Right, so I want to talk about 2 things. So the first is the parent Hamiltonian. I want to talk about the holographic principle in tensor networks, and I want to talk about the possibility of, showing that they correspond to this corner of Hilbert space. That's my goal for today. So I'll talk first about the parent Hamiltonian. So at the moment, what I say that if you have a Hamiltonian which is local, like the one, then you may try to approximate in terms of these tensor networks, which you can write something like that, maybe. And I told you when it's claimed that it works, and when nothing is claimed, there are only practitioners that do that. But now I want to ask the opposite question. So if I have a tensor network, can I find a Hamiltonian for which it's local, for which I can promise that this will be the ground state and even the unique ground state for that? And that's what is called the parent Hamiltonian, and there's a construction for that I want to mention. And the idea is relatively simple. I do it in 1 dimension, but it works for any dimension. Imagine that you give me this tensor network. Sample this one here with all the tensors the same, so that it's homogeneous. Now, what you may notice is that these indices here run from 1 to d. This is the physical dimension, so these are like the speeds, the original speeds. And these indices here, this is people call the virtual dimension, d. That's the one that we include this direction in the tensor that didn't have to do anything with physics, which is there. And you see that if we start blocking tensors, so we get what I told you before, joining these tensors, I can have a bigger tensor, where now this dimension here would be d to the L, so if I block L, whereas this one here will still be d and d squared. So if I start blocking and blocking and blocking, at some point, this dimension here would be larger than the dimension over here, right? Because this grows like the number of sides, and the other one is constant. If you go to 2 dimensions, you can do something similar, because you put together different tensors, then the dimension of the physical indices will work like the volume, whereas these auxiliary indices will grow like the surface. So volume always grows faster than the surface, so there will be some time at which you will have like a bigger space here than the space on the virtual indices. And now, I don't have time to tell you, but so what this means is that if you consider a map that goes from the auxiliary indices to these physical indices, that is here, then this map has to be left invertible. Or in other words, it has to have a kernel. So you have a map that goes from a dimension of a space that is very small to a dimension which is very big, then there will be something, sorry, the other way around, I'm sorry. So you have a map that goes from a big space to some small space, then there might happen that some of the maps have to go to the same point, and so you take the difference, you have a linear space, the difference of these two will be mapped to 0. So this means that there will be a kernel. If it means a kernel, it means that you can apply here some operator in such a way that this operator acting on this will be equal to 0. Call it x. Okay, so you start drawing what I'm saying, that there is a point where this dimension here is bigger than this dimension here, so it must happen that there is an operator which is mapped to 0, which gives 0. Then you can take this operator and write a positive operator out of that. So you can take O and write O dark O. That's a positive semi-definite operator, it's always positive. And now you can take this operator, let me call it P, and this is a position I. Let me take all the i's that are possible, and let me sum with respect to the all i's. And let me call this my Hamiltonian. And what you can show is that each of the terms by construction is 0. So the sum will be 0. On top of that, these are positive semi-definite. So all the eigenvalues of these operators are positive or 0. And the sum of operators whose eigenvalues are positive or 0 are also positive or 0. This means that this Hamiltonian is positive semi-definite. The spectrum only contains 0 and positive numbers. Automatically, this must be a ground state. Now, this doesn't ensure so this was, I should put it here. This was parent Hamiltonians. Right? So these are Hamiltonians which are positive and fulfill that h psi is equal to 0 in any dimension, and I will write it here plus some conditions. Some technical conditions is unique. Ground state. Now, the next step that I want to do with this method, so maybe to recapitulate, because I'm giving a lot of information. So I introduced this notation. I promise that this corresponds to this corner of Hilbert space. I didn't show it. Assuming that this is the corner of Hilbert space, I told you, okay, then it can be used in order to compute ground states of these many-body systems. And you can compute with the algorithm that I told you, these variational algorithms, standard algorithms. You can apply them here, and then you will be able to compute some properties. In one dimension, this method solves all gap Hamiltonians efficiently. In higher dimensions, there is no proof for that, but people are able to solve models in 2 dimensions with this method. I also told you now that apart from using it for numerics, you can, just given the tensor networks, you can build Hamiltonians. You can back construct problems for which you have the solution. And once you have the solution, then you can compute expectation values. Now, I want to talk about two properties. One is the bulk boundary, so properties of these tensor networks. So the first one is the bulk boundary correspondence. And the second one that I want to briefly talk is about symmetries. And so, what about bulk boundary correspondence? So imagine that I have a tensor network, and let me put it in a cylinder. Okay, so now I consider a two-dimensional system with a geometry corresponding to a cylinder. So I have a lattice with periodic boundary conditions in one direction and open boundary conditions in the other direction. Just like that. So these are your edges and so on. And now what I want to do is I want to consider now some region of space here. For example, this region of space, the region A. And I will write a single tensor for this region of space. And so consider the cylinder, I get around, and this corresponds to the region of space, and the rest will be the complement of the region of space. So, you see, for this first region of space, I can consider all the tensors. I put them together, I merge them in the way that I told you before, and so what they will have are the physical indices. So there will be a physical index here, corresponding to all the arrows that are here, now that they're in a single index. Now, for the second part, right here, the second part B, I can do the same thing. So I have some other physical index, and then these are now contracted according to these indices that cross these two regions. Okay, so I tell you that I have the tensor networks, and I consider like two regions, A and B. And so the first thing that we notice here is that, so this physical index, what is the dimension of this physical index? Let's count. So we have put together all the indices that are across this region. So this will be like for each of the index, every time that we put an index, we multiply. So if it's an index D, it will be D, 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 D. So it will be D to the power the perimeter of this circle. And here, it will be the physical dimension to the volume of A, put it like that. And this will be D to the power volume of B. Okay, so I have simplified, instead of writing many indices, I will put them together. And now, so what happens if I compute the reduced state of this picture? This means that what I want to do is now to take the state corresponding to that, which is written like that, and I want to now trace the second system in order to compute what is the reduced state with respect of A. And so what I will have to do, now we can do it with a drawing as well. So we have to take the region D, B, have to put the same psi, which I represented like that. There is this index. And now tracing means that I am just contracting this index here. And so this is the way in which we will represent this index here. Sorry, this reduced density operator. And now you can ask, so what is the entropy of this rho A? You can compute the entropy of rho A. And this entropy of rho A is nothing else, according to what we said before, that the entanglement between the region A and B. This is the entanglement entropy of the region A and B, and the complement. And, well, I want to explain it in detail, but you see that here I have a big dimensional system. This is this D to the volume of A. And now this is a matrix. It's a matrix multiplication that is here. So you can read it as a tensor network in which you have a matrix, a matrix, a matrix, a matrix. So you see that this reduced state, this rho A, is a product of matrices. So it has the matrix here, so it has this big index here. Now it has this matrix with a small index. Then you have a matrix with a big index. This is the one of the physical dimension of the second system. Then it has another one small, and this one here. And when you have matrices and you multiply matrices, the rank of the matrix is limited by the minimal rank of the matrices that you're multiplying. So this means that this matrix will have all eigenvalues equal to 0, except at most the ones that are here, which is the minimal index. So this means that this state, now the minimal entropy, the entropy of this state cannot be larger than the dimension where it lives, and the dimension where it lives is limited by this to the power, and we call it perimeter, P. So the entropy of that is smaller or equal than the log of this quantity, the log of the dimension of the Hilbert space, so P times some log of T. So you see that the entanglement entropy between a region and the rest is limited by the perimeter. So it fulfills an area law. And you can do it in general. Just take any area. They consider this as the indices of this area. And the rest, these are these, that are connected by the boundaries. And the entropy is just limited, is just upper bounded by the number of bonds that are connecting these two regions. And so it means that these tensor networks fulfill an area law. All of them, just by construction. So the first thing is that all tensor networks fulfill an area law. But of course, this, what we would like to show is just the opposite. This is what comes later on, that if they fulfill an area law, that you can have this, description. But what is more important is that now, so if you can, let me do it graphically. So maybe it's difficult to understand, I'm aware of that. But I want to show. So imagine now that I want to compute an expectation value in some region A. So I put some operator in A, and then I will compute the expectation value of this operator with the whole state. It means that I have this region A, so again we have the cylinder, or could be anything. We take some region A, and we would like to compute an expectation value of an observable in this region A. So what I will have to do is to take the region A, put all the indices together, then the connection with the complement does the tensor corresponding to region B. These are the indices of region B. So again, so this is the lattice, this is the region A. Then we have the physical indices here, the ones that are coming out in this tensor network. We put them together, this is this index. Then in the region B, we have all the physical indices coming out. We put them together, that's these indices. And then they are connected by these auxiliary indices. And this is this. So this scales like the number of, well, this dimension of that is this d to the power of the perimeter. So that's similar to what we did before. And now to compute an expectation value for some region A, I put some observable in region A, and then I have to contract it in the way I told you that I have to contract. So just like that, but that, and I contract these indices, and that's a number, because I have all the indices contracted in one way or another one. And so what you can see is that actually this quantity can be interpreted as having now this tensor, so just consider these tensors on the left, and putting some operator in this tensor. So we call this O tilde, with this one operator, which comes here, which is just this one here. And so what we have is that now we can compute the same expectation value, but on a system which has the physical indices, or the state act on the boundary. So anything that you want to compute in the bulk can be computed in the boundary. So there is a boundary theory, or in other words, you can define for any region some other state that lives on the boundary, And then you can compute any expectation value of the bulk by the boundary. And that's what is called the bulk boundary correspondence. So any computation, any tensor networks has this holographic principle in which you can show just by construction that for any region of space, all the information is in a theory that lives in the boundary. And with this state that lives in the boundary, you can compute everything that is on the bulk. That's what this. And you do this mapping to the boundary, then it's like computing something in one dimension, and for this one dimension, you use this technique that I told you with matrix product state. If you are in 3 dimensions, then you can compute something in the boundary in 3 dimensions of the region, which is a 2 dimension. And when you want to compute something in the boundary in 2 dimensions, they can compute it in the boundary of the boundary to go to 1 dimension. And so the algorithms that work in practice for this tensor network use this dimensional reduction. But not only that, it also tells you that now you have something like a holographic principle. And so for the people who know about that, if you have now some topological theory or something like that, then we know that there is a bulk boundary correspondence, and this gives you this bulk boundary correspondence. So you compute now entanglement spectrums and so on, then you will see that you have a topological theory, you get a conformal field theory in the boundary, and these things is included here. So I just wanted to mention that it comes in a very natural way just by this construction. By the fact that you have these physical indices and these auxiliary indices, which you promote to something that is physical, which is the boundary, and so this gives you this kind of holographic principle for tensor networks. Okay, so now the other thing that I wanted to mention are symmetries. And through symmetries, I would like to finish talking about topology. I know that I'm going very fast, but I know that there is a session of questions, so if somebody wants to learn a little bit more, then I can explain a little bit more in detail in the session of questions. I want to present the menu here. And so the other one is obviously 2, which are symmetries. And the idea for the symmetries is that imagine that you have a global symmetry. For example, this means that you have a state psi, you have a group G, and then you take an element of the group, you have a representation of the group, a unitary representation of the group, UG, that is act on one side, you have a global, so it's acting on all sides, and this state is invariant under this symmetry. Right? So that's what we say, that the state is invariant under the action of this representation of the group, the physical index. So how do we understand symmetries in tensor networks? Well, let's do it with a one-dimensional system that is the same in higher dimensional system. So let's take the representation of our tensor network, and let's imagine that it's translational invariant, so that all the tensors are the same. So in the language of tensor networks, what we are doing is saying that applying U to each of the physical indices, so applying UG here, UG here, UG here, UG here, which are matrices, so I should represent it like that, then the state remains invariant. Doesn't change. And now you can formulate this mathematically and prove that this means that this tensor has to be equal to the tensor without the U, except that you have changed, you may have made a gauge transformation. So you will understand what I mean. So out of that, it follows that the tensor, if I apply this U, this has to be equal to apply here some V, G, and VG dagger. And you see why this has to be like that? Because you see, imagine that I apply this here, and indeed, this is the same thing as erasing that, and putting here some VG, V, and V dagger. I can do the same thing here. If this is true, then I can get rid of that and put here V, V dagger. And every time that I erase that, if something like that is true, it means that I will have something like VV dagger. But if this is a unitary operator, VV dagger is the identity. So I can erase VV dagger, and so I have this invariance. So this is one direction of the group. If this is true and this is true, you can also prove the opposite. Okay? So if this is true, this is true. And this means that in tensor networks, global symmetry are represented in terms of local symmetries of your tensor, but very funny symmetries. And so now for the experts on cohomologies and things like that, then you see that this, I mean, you can show that if this is a representation of your group, this is a representation of your group. So if G1, G2 is equal to G3, then UG1 times UG2 is equal to UG3. That's a representation. But the VG1 times VG2 has to be equal to VG3 up to a phase. Because you see that I have here V and V dagger. So there is a phase that is not defined. So this means that this is a projective representation of your group. And so it means that the symmetries of your system appear as projective representations of your group in terms of the tensors. And now you can understand qualitatively that if you want to classify symmetries, so you want to classify states that have symmetries in terms of tensor networks, you will have to classify the projective representations of the group, and the projective representations of a group in this form is the second cohomology class. And this is why people will tell you that if you have symmetries in your system and you want to make this periodic table that I told you before, in which you look at how you can have the different symmetries in your physical space, the physical symmetries in the space are classified with the second cohomology class of your group in one dimension, with the third in two dimensions, and so on. So this makes a connection with tensor networks, with symmetries, and with phases, and with a classification of phases. This is what is called SPT phases, which was done first classification using tensor networks, using this thing. And this tells you that these tensor networks can be a numerical tool, but this, what I told you before, it's also a classification way. So you can classify now tensor, you can consider all possible tensors that fulfill this property. You put here any group, you put here any representation, a projective representation of your group, and you can generate the different phases corresponding to the different symmetries. And people have done that in the past. You can go to higher dimensions, and the same thing is true. So that's what I wanted to say about symmetries. You can also have gauge symmetries. So, for example, imagine that now you're considering what I told at the beginning, that your lattice has, something that I didn't mention. I work all the time with spins, but you can represent fermions. The only thing is that these tensors now will be made out of Grassmann variables. So you can, let's just copy one to one, but you have to take into account that they have anti-commutation relation. It tells you that external numbers have to work with Grassmann variables. Now, if you have fermions, a fermion lattice with a gauge field, so you will represent it in this form, where, right, so for example, these are the lattices in which you have, I mentioned before, one dimensional, the vertices are matter, are fermions, and in the edges you have gauge fields. So now you will have associate fermionic degrees of freedom to these indices, bosonic to these indices, fermionic, bosonic, fermionic. And now a gauge symmetry means that again you have a gauge group, you have a group, and you have a representation of this group, which is acting both in the matter and the field degrees of freedom. And whenever you apply some U, V, U here, then the state remains invariant. Right? So you have some local symmetry, it's not a global, now it's acting locally. And now if you have a local symmetry, then you can impose what are the conditions for these tensors to fulfill this condition, and then you get similar equations to this one, in which now, of course, they are working with Grassmann variables and so on, but this means that this is the way in which people represent now gauge theories, in which the Gauss law, so the gauge symmetry, is already included in the representation of tensors. You don't have to impose anything, so directly there you choose the tensors in the particular way. And okay, so I wanted to talk about topology, topological order with this language, which is in terms of strings that you can move and so on, so it has a very nice representation, but I will now talk about this corner of Hilbert space. And so that's what I call efficient representations. And there are two ways, so again, so coming to this plot, And I would like to show that the guys that live in this corner can be represented as tensor networks. And so what I'm going to do, I mean the proofs are very difficult, but I'm going to just give you an idea of how this can be done. And this can be done in two ways. One is through area loss, and the other one is just explicit construction. I'm going to do it with explicit construction. And because it's, simpler, and the proofs that the most powerful proofs come from these explicit constructions. So what I want to show is that e to the minus beta h like that, I can get this state just by a purification, and that's always possible. So if I have a system in a mixed state, A, I can always add another system, auxiliary system B, consider a pure state here, in such a way that if I can compute the reduced state of A, it's equal to my original state. That's what is called purification. Any mixed state can be written in terms of a pure state if you double the dimensions of your system. And in particular, the state that would give rise to this, so the purification of this operator, can be very easily written. You just start with maximal entangled states. So you start, this is your system, your qubits or whatever, in one dimension or any higher dimension. Then you put a copy for your system. This is the new system B in each of the systems. And then you consider that they are originally in a maximally entangled state. I already defined what is a maximally entangled state. This is the sum of n that I wrote at the beginning. So you consider a state which will be the state phi plus, but that is n times, because there are n of those. Okay, this contains the system, and this is called ancilla, the auxiliary system. And what I do now is that I'm going to apply an operator e to the minus beta h to my system, each house, in fact, and nothing to the second system. So apply this operator to this part. And you see that if I consider this as a state psi, if I compute the trace with respect of B of psi, it's very simple that you will put just the opposite. When you compute the trace of that is the identity operator, so this gives e to the minus beta h. So this psi is a purification of my Gibbs state. And now, the only thing that I have to do is to read this formula. In this formula, I have this operator, exponential, but now I'm considering that this operator is a sum of operators that commute. So the exponential of a sum of operators that commute is the product of the exponential. So I can write this as e to the minus beta h1 times e to the minus beta h2, etc., etc. Phi plus. And now you see that what I'm doing is that I'm taking this state, so let me just write it as a tensor network. So this is a state which has two indices, is a product state, has corresponding to these two. This has two indices, and I have another two indices here, and I have another two indices here, and so on. And then what I'm doing is that I'm applying a Hamiltonian corresponding to the first two systems, or the first few systems. So what I'm applying here is some tensor which is acting on this index, and doing something like that. And this is a finite dimension, so this is the dimension of my cubit. With the next one. So you see that by construction I can put things together, and so this is nothing else than something like that. Where this is a fixed dimension. It just does not have to do anything with the dimension of the Hilbert space with anything. It has the dimension, the physical dimension of 2 qubits, let's say 4. It's 4. So what you show is that indeed this pure last statement. So what happens if, and that's the complicated third case, and this is what you can find in this review more efficient. So what happens if the Hamiltonians don't commute, which is the general case? If they don't commute, then the idea is to say, let me take y minus beta h, and let's do in the same way that I told you that people do in Monte Carlo, which is this totalization. Let's divide it by L, and let's take y minus beta h divided by L, so we have a product of L of those. And now, since L, if L is very big, then you can consider this to commute with each other, because the commutator, which is the correction, will be higher order in 1 over L, will run like 1 over L squared. So then you can approximate very well by things that commute. The price that you have to pay is that now, instead of having this operation that I did before, you will have, with commuting Hamiltonians, you will have to do it L times. So now, you can think, well, so now I have to do it L times, so at the end I will have L of those, So the dimension here would be some fixed dimension to the power L. That's very bad, because in order for this approximation to be true, this has to scale with n. So it will be something. So what you can do is to compress those and still get something that grows only polynomially. And so at the end, that's the proof that tells you that everything can be written in terms of tensor networks in an efficient way. So summarizing, okay. So what I was finding here is that, so I talk about tensor networks. That's a language to describe many-body systems, and it's a language that if you have a small bond dimension, if your capital D does not grow exponentially, then it allows you to describe states very efficiently. Now, I told you that once you have this description, then you can use for numerical methods, because the contraction and computation of expectation values, you can do it without having to go to Hilbert space. You can do it directly with the tensors, and this gives rise to numerical algorithms. On the other hand, I also told you that you can consider the tensors themselves, and now by looking at the tensors themselves, you can study things like symmetry, topology, and so on, because they are represented like symmetries of your tensors. I mean, projective representations, not representations. If you have now a topological order, then what will happen is that you will have some symmetries, and what happens is that they represent, when they then these tensors give you representations of tensor categories or width of algebras and so on, which I mean, gives you the topological order are described in terms of that. So this comes in a very natural way. I will also tell you that as long as you have some finite temperature here, then you can prove that you're in this corner of the space, that you need only polynomial dimension. What I didn't mention is that if you take, with this construction, the limit equal to infinite, then the one dimension is infinite, because there is a beta that appears somewhere. So this doesn't work for zero temperature. You have to use other methods to try to prove whether this also works at zero temperature. And so I also want to say that, of course, this gives you a lot of mileage to study things, but it's not everything. There are things that are not yet solved with this kind of language. For example, one of them that is very important is if you have chiral topological order, like you have in fractional quantum Hall effect and so on, then people, have figured out that these tensor networks, whenever you try to describe chiral topological order, you can describe, but the tensor networks that you have polar correlations, not exponential correlations. And so people are trying to either prove or disprove or find ways in order to describe this chiral topological order with these tensor networks, and many other open questions and still remain. So this finishes today's lecture, and so tomorrow I will forget about tensor networks, I will go back to the problems, and then I will use a quantum computer to solve those. Well, I will not use a quantum computer, I will tell you how a quantum computer could be used in order to solve some of those problems.
Question time.
So I have a technical curiosity.
Yep.
You mentioned the fact that you can express in terms of tensor networks the classification of projective representation, some impacting on the physics. This means that there should be a way of classifying the central extensions, no, of the group in terms of, or not. There is some literature on that?
Probably, but I don't know about that. I don't know about that. So what I was telling you is that if you have global symmetries and you impose that you have global symmetries, then you can define an equivalence relation that two states are of the same phase, that's the equivalence relation, if they have the same symmetry and they are connected adiabatically with each other. I didn't mention it here. This gives you classification, this gives an equivalence relation, therefore this gives you a classification. This classification is called symmetry protected topological phases, and this classification is characterized by the second cohomology class in one dimension. It's not that you have a representation of the, well, in each of these phases, let's say, you will have a representation of the projective group, which will be the operators that appear on the sides whenever you have this symmetry. This happens. Now, if out of that, then there's a way of extracting what is the central extension. I'm not familiar with that, so maybe, and yeah, that's what as much as I can say.
First, just to be sure, when you say a local Hamiltonian, you mean that, well, in the continuum limit would be with a finite number of derivatives.
Exactly.
In the discrete, in the lattice setting, it means it has only nearest neighbors or interactions or a finite number.
Finite range. It's a finite range interaction.
Yeah.
That's right.
So, I'm trying to understand why these tensor networks describe well that corner of physical interest. Is it because we are interested in physical models where the Hamiltonian is of this type? I mean, and the geometry, the connectivity of the tensor network exactly is the same, corresponds to that of the interaction terms in the Hamiltonian. So if for instance you have a two-dimensional lattice and each side interacts with the nearest neighbors, you need a matrix. I mean, four indices, so to say. If you have three-dimensional, is it?
It's related to that. So I mean, since here you see they are acting on a region,
yeah,
then it doesn't matter what is the geometry that is embedding them, because you could block and at the end you can map everything to something which is effectively something like a square lattice. But indeed, At the end, what happens is that since they're acting in some regions, then this defines some geometry, and this geometry is the ones that defines what are the tensors that are coming out. And in 3 dimensions, there will be the tensor which will have now significances, like the coordination number. So that's the way it works. And in this construction that I made here, it explicitly uses that in order to show that you're in your corner. So you would have some long-range interactions, for example, then this will not be true, and this will not work, because then you will have some index, some tensor that will join this one here and this one here, and this will have to go through all the other ones, and this will increase the bond dimension, let's say, linearly, exponentially with them. So I mean, the claims are all of them for Hamiltonians, which are what is called geometrically local, meaning that are finite range interactions. Now, this can be extended, so people have extended this to Hamiltonian that have exponentially decaying tails. So that's very trivial because at the end you can just cut the tails and then it's a logarithmic level or whatever. So, and some people have worked, but I'm not so much aware of that. You have certain power laws and the power laws of usually large.
You mentioned this nice parallel between the tensor networks and the orographic principle, right?
And then?
Orographic principle.
Yes.
So I just wanted to understand a little bit better the statement, because something very important when we call orographic principle, for instance, in the context of a SFT, is that in the bulk we have gravity, so that we don't have observables in the bulk. All the observables are indeed at the boundary. But in the context of these tensor networks, so there are some states which are desired law, I guess they are completely captured by the boundary, but there would also be, I want to understand.
Yeah, but this is like if you would have now a physical quantum indices in the bulk, like quantum gravity.
Yeah, but so what is the analogy? Because gravity tells you that there is no bulk observable. And what is here that is cancelling or, because you can also formulate the SFT with the bulk QFT.
Yes.
Then you're, but in this case, you are just taking the boundary limit of some bulk observables,
yep.
And there are other observables which will not be orographic.
So, okay, so I'm not an expert on that, but I can tell you is the following. So, first of all, that what you say is a construction that people have done with other tensor networks that are called MERA, and that there is no physical indices. These are like tensor trees that go, and they have the indices in the boundary. These should correspond to the CFT part. And then, I mean, they are related to gravity, to this previous Tanaka-Galli formula, and so there is a formulation. But, and probably you know that if you, I mean, cut these tensor networks, this corresponds to black holes and so on, and so people have been working on these things. But as far as I understood, I mean, there are some other people who have put indices to the bulk, and the indices to the bulk would correspond to now to observables that would compute, let's say, in quantum gravity, in a sense. What is not clear, and that's case that this is what people are trying, some of them trying to see in the model, is that there is a kind of locality enforced. So you have something that is local in the gravity side, that it would be local, but I mean, this of course would, I mean, you would do the whole thing is making sure that it's conformal, which is not the case. Then would, I mean, you have a quantum gravity, which does not exist, no? But that's one way that people are trying to.
Maybe my question is a little bit more technical.
Yeah.
So in ADS-CFT, I can try to compute an orographic observable for a theory that is not gravity in the box.
Yes.
I would just get some boundary limit of some bulk observable, and that would give you some CFT, which is non-local, etc.
Yep.
So, I have both options.
Yep.
And here, do I also have both options?
Well,
so only because I don't understand what replaces gravity in the context of this.
Okay, so here I never mentioned gravity in explicitly because it's just that there is a mapping between bulk and boundary. So you have a quantum degrees of freedom, like a quantum mechanics. Let's say on a bulk, then I can write, when you give me a state, I can write some of the state which lives in the boundary, and I have a one-to-one correspondence. It's not one-to-one, it's n-to-one correspondence. Anything that can be computed in the theory in the bulk can be computed in the boundary. So here, there is nothing about conformal theory, there is not any ADS, so the geometry here is a square lattice, it's not a hyperbolic geometry, and nothing like that. So now, if you want to make the connection to ADS-CFT, then you probably have to read some other papers or attend some other talks, because there are experts who are doing that, and I know that this is satisfactory to some extent, but there are people who are saying that this is not very satisfactory because some things are missing. For example, one of them is that you have to have a CFT. And CFT probably have to work in the continuum, because otherwise the discretization to CFT may not be that good. And to go to the continuum, you have something which are called continuum matrix coalescence or continuum PEPs and so on that exist. However, this continuous mirror, which is like that, loses some of the properties, and it is not satisfactory. And so there are many questions, and these black holes that people have done, by putting random tensors and things like that, have done, but it doesn't seem that you can fulfill all the requirements that you should fulfill in order to have an ADS-CFT correspondence with these tensor networks. But, I mean, I'm here talking about something which is not ADS-CFT correspondence. We have lattice-based theories. And you have a state of that in that lattice-based theory, and I promise you that whatever you can compute in the bulk, I can compute it in the boundary.
For that state. So
for that state. It's state dependent.
So maybe that's the answer to my question. There are other states that would
all the states would be another correspondence. Yeah. Right.
I have an easy question. We have been talking about mixed states and also entangled states. Yeah. Are they the same or is this?
No. So you have two systems. They can be entangled and they can be pure. However, if you discard one system and you look at a single one, then you will have a mixed state. So whenever you have a mixed state, you can think of this mixed state to be the result of having a pure state with some auxiliary system in which you discard the auxiliary system. So for example, when I was doing this construction here that I mentioned, you see, I started with some mixed state of a single system, and I constructed a pure state of a system and a copy, and I tell you that I will get the mixed state if you have entanglement in this system and throw the second system. So there is a connection between the entanglement and the mixed state, and in fact, I mean, the measure of entanglement that I was defining tells you that entanglement is related to the mixedness of the mixed state that corresponds to that.
So I know a mixed state is defined by a density matrix
that
is not diagonal.
No, it's not that it's not diagonal, it's a density matrix that has a rank different than 1. It's not a one-rank projector. It's not a rank 1 projector.
It's not a matrix which is 1 and everything is 0.
No, so it has more than one eigenvalue, different than 0.
I have a question about your approach to parameter Hamiltonian.
Yeah.
Does that argument work only for matrix product state, or it can be generalized also to PEPs?
Well, works with PEPs. It works with PEPs because of what I told you. So if I start blocking, at some point the physical indices grow like the volume, like the exponential of the volume. The other one is the exponential of the surface. So if I block a number, a large enough number, then I will have that the dimension of the space of the physical indices is larger than the other one, and therefore there should be a kernel. So there should be an operator which is mapped to 0. And once you have this kernel, then you have the parent Hamiltonian.
I'm confused about that little corner of the Hilbert space. So, which is the precise? I'm sure that you told me that, but maybe I'm confused. So, what is the relationship between being area low state and having tensor network representation? So, which is the exact kind of relationship? Okay, so I was mentioning here and there, and I was planning to make a connection, but I was running out of time, and I decided to go the shortcut. Okay. So the idea is that you have, by counting argument that I gave at the beginning, there is this corner of Hilbert space with all physics appears, not only for ground states, also for dynamics. There is always a corner of Hilbert space because of counting parameters. So the question is if you can get hold of this corner of Hilbert space. So can I find a description that would be very bad for anything that is outside, but for this corner work will work. And one possibility is to identify one condition that all the states in this corner fulfill, and to find a representation that for all states fulfilling that condition is efficient. Okay, so you're able to find a property of all the states that live there that is that is always true there and may not be true outside. and then you find a representation that all the states which fulfill that condition, then it's efficient, and you have a hole on this corner of the space. This condition was identified many years ago. This is this area law. Okay? And so this means that, and also you can think of two ways. One of them is if you have a state in the corner of the space and fulfills an area law, and that's what I mentioned before, that can be done in terms of the mutual information. You can prove it with these free energies that I did this before. For pure states, people have proved it here and there. I mentioned something like that. You identify this property. So now this guides you to how to represent this corner of Hilbert space. So how to build all the states that would fulfill this area law, and this gives rise to the tensor network. I didn't explain that. I didn't explain that, but that's one way, or to get inspired to build that and then try to prove that all of them are like that. What I did is just the opposite. I took tensor networks and I showed that all of them fulfill the area law, and all of them have parent Hamiltonians which are local. Of course, very interesting the other one, but I didn't prove that. And this is much more difficult, and people have not proven full generality. So I decided to prove this, the connection not through the area law, but direct construction. This is what I call direct construction. What I say, let me take the given state, and let me show directly that this can be efficiently described as long as this beta is not infinite, or any value. And that's how I did it. But so I was mixing up the two things, but the first one of the area law is because this is the one that people identified, that was the important one, and people came up with tensor networks, they proved it here and there, but then they found a more direct and more powerful way of proving things, which is through this.
Amazing, thank you.
In your construction of the parent Hamiltonian, can you say at the end that it's gapped, or can you say anything?
And in one dimension, I can promise you that is gapped if the tensor fulfills certain conditions, which is called normality. So there is, so in this tensor, I told you that if I start putting them together, combining them, at some point, the dimension of the physical Hilbert space grows faster than the dimension of the auxiliary Hilbert. And so now, if this mapping between the auxiliary indices to the physical index, I mean the tensor is just like we consider as a mapping. If this mapping is injective, then you can prove that is a unique ground state, and you can prove in one dimension that is gap. If this is not fulfilled, so if this map is not injective, then you can show that it cannot be the ground state of any local Hamiltonian unique. It must always be some degeneracy. Now, if you have this property that in higher dimensions, so you have this injectivity property in higher than one dimension, then this is not sufficient to prove that the gap persists in the thermodynamic limit. You can prove that there is a unique ground state for any finite system, but it may happen that the gap closes in the thermodynamic limit. You need some other condition. You can use some bootstrap kind of method to get another condition that will ensure that you have a gap on top. So the short summary is yes, but. So you can put some conditions that ensure that you have a gap and you have a unique ground state. Or that you have a degenerate state with a gap, like in topological states, they have degeneracy of the ground state, but there is a gap on top.
How difficult is to compute the minimum of the energy for the variational approach you used before? I mean, you use a standard guide essence.
No, you use something, now technically speaking, it's called density matrix renormalization group. It's a method that does it sequentially. So you have many tensors, and then you have to minimize with respect to all the possible tensors. So what you do is that put some random tensors, and you take the first one and minimize with the first one. You fix this one, then go to the next one, and then you go back and forth. And this actually gets still stuck in some local minimum. So in order to make sure that you don't get stuck in some more local minimum, there is a way of doing that, theoretically, which is, I'm not going to describe, it's complicated, but in practice, the practitioners, what they do is that they grow the system. So they start with 2 qubits, they want to go to 22 qubits. They start with 2 qubits, and they start just doing this swapping. Then they put a 3rd qubit, continue, 4th qubit, continue. In practice, works very well, and that's what is called the emerging, the density matrix emerging group. It's a way of doing this minimization that is peculiar, and it works very well in practice.
And you do not have programs such as bar and plateau for quantum?
Not for the typical examples that appear in tensor networks, not at all. In one dimension. In higher dimension, it has been much less studied. So in one dimension, I would tell you that, I mean, because we have codes and so on, and so they never get stuck in bar and plateau, and the gradients nor anything else. I mean, there is a way. You don't do it through gradients. I mean, you don't do the variation just by taking the manifold and projecting and so on like that. You do it in a better way, which is that you solve for all the values at the same time. It's like a second order Hessian project with a whole tensor each time. And by doing that, you escape many of these problems.
Other questions? I have a question. Going back to the parent Hamiltonian problem. So now you have a Hamiltonian that is local, but in this new physical index that is the one where you block things together, right?
Yes,
right.
Yes.
Because
right.
This kernel operator.
Right. Well, it's acting in the indices that you put together. So you, of course, you touch them again, and then it's a Hamiltonian which is acting.
It's local, but a bit less, right? Because it is
right, but it's still local. It's acting on few because we know that we have to. I mean, we know that since one grows like the flower at the other the surface, you know that after a constant of time, so you have a physical dimension, one dimension, after a constant time, you will satisfy that, so we'll act on a constant region, so we'll have a finite range, which is constantly independent of the size of the system.
Very good. And now your Hamiltonian is the sum of these terms.
That's right.
That act, and they act on different sides.
Exactly.
So they automatically commute.
No, because they have overlaps.
Okay.
So you block, find the Hamiltonian. Okay, you have four sides. Okay, you block these three, make the Hamiltonian acting three. Then you take these three, make a Hamiltonian. Then you take the next three, make the Hamiltonian. It has to be like that. So I was not explicit. It's not that you block and they are independent, so they overlap, and so they don't commute. Yes, otherwise it would be bad because we know that if we have commuting Hamiltonians, then you have zero correlation length. So therefore, with this, you could only describe state with zero correlation length, which would be very useless.
No, that's why I was thinking of that because of the question about how, whether there is a gap or not, because this would ensure that there is a gap.
This ensures that there is a gap, but it's not.
More questions? Okay, I think we can thank Professor Cirara for and we will reconvene tomorrow at 10 for the final third lecture, which is again in 2 parts.